Good morning. My name is Mudawat Lakshman and I'm from CSC F section. So today I'm going to discuss about random variable transformation in load uncertainty modeling of suspension bridge from the subject probability and statistics. So introduction to load uncertainty in suspension bridges. Suspension bridges are exposed to variable loads such as wind, traffic, temperature and material fatigue. These loads are uncertain and vary with time, many making their accurate prediction challenging. Modeling such as uncertainties is essential for ensuring bridge safety, performance, and reliability. The use of random variables allow engineers to represent these uncertainties mathematically to perform probabilistic analysis for better design and maintenance strategies. So now, suspension bridges are constantly exposed to varying loads such as wind, vehicle traffic, temperature changes, and material fatigue. These loads are not constant, they change over time, are influenced by unpredictable environment conditions. Hence, it is important to model them as random variable to account for uncertainty in the magnitude and frequency. Accurate modeling of these uncertainties ensures the bridge's safety, reliability, and performance over its lifetime. By using probabilistic methods, engineers can design structures and remain stable even under uncertain fluctuating loads. So now, what are the basic concepts of random variable? A random variable is a quantity that takes different values based on chance or probability. Two main types are discrete and continuous random variable. Each variable has a probability distribution: normal, log normal, and variable. These are the examples. In engineering, load effects are modeled as random variables due to inherent uncertainty. The mean, variance, probability, and density function describes its behavior. So here, a random variable represents a quantity that can take different values according to probability rule. In bridge engineering, loads such as wind force or vehicle weightage are treated as random variables because they are unpredictable. So they are unpredictable. These variables can be discrete, such as a number of vehicles on the bridge, or continuous, like wind speed. Each random variable has an associated probability distribution, such as normal, log normal, or variable. You can say that log normal as variable that defines its behavior. Important statistical properties like mean, variance, PDB, PDF. So I mean to say probability density function help describes their expected range and likelihood, which are crucial for reliability and modeling. So now we are going to discuss what is the purpose of variable transformation. In many engineering applications, it is necessary to convert one random variable into another form to simplify analysis or match known probability distributions. Variable transformation helps convert complex non-normal variables into standard forms like the normal distribution, enabling easier computational of reliability, sensitivity, and safety indices. These techniques is vital in suspension bridge modeling to handle complex load patterns influenced by multiple uncertain parameters. In many engineering applications, we often need to convert one type of random variable into another to simplify analysis. For instance, real-world data may follow a non-normal distribution, making it hard to use standard reliability equations. Through variable transformation, we convert these complex random variables into standard forms such as normal or uniform distribution, which are easier to analyze. In suspension bridge modeling, this approach allows engineers to study the effect of wind and traffic loads efficiently. Even when these loads are irregular or combined, the transformation helps achieve mathematical simplicity and computational efficiency. So now, common random variable transformation. What are the common random variable transformation? Linear transformations that are scaling and shifting the random variable. Logarithmic transformation used for manipulative multiplicative uncertainty or skewed data. Power transformation, stability variance in nonlinear models. Normalizing transform converts any variable to standard normal form. Nonlinear mappings applied when load effects or nonlinear dependencies. So here, linear transformation adjusts the scale and the location of the variable. Logarithmic transformation, it handles the skewed data or multiplicative uncertainties, commonly used for wind pressures, we know. Power transformation stabilizes variance in nonlinear models. Normalization converts random variable into standard normal form of statistical analysis. Nonlinear mapping. It deals with the interdependent or high variable data. These transformations allow engineers to handle a wide range of uncertain load behaviors effectively, preparing them for reliability studies. So next we are going to know about the probability integral transform. Probability integral transform. The probability integral transform PIT states that if a random variable x and x has cumulative distribution x of x, that is distribution function CDF, that we know, um, like okay, f of x and f of x of x, then u equal to f of x of x, u equal to f of x of x is uniformly distributed on 0, 1. This technique is fundamental for converting variables from one distribution to another, especially in stochastic simulations. In bridge modeling, PIT helps map uncertain load parameters to uniform or normal distributions for probabilistic analysis, right? So the probability integral transform is a mathematical technique that converts any random variable into a uniform distribution between 0 and 1. If the variable x has a cumulative difference function fx of x, then u equal to fx of x becomes uniformly distributed on 0 and 1. This concept is essential for transforming variables from one probability distribution to another, right? In suspension bridge modeling, PIT helps map uncertain parameters like random wind or traffic effects into standard distributions that are easier to handle in stochastic simulations and probabilistic reliability analysis. So next, inverse transform method used to generate random samples from a known distribution. So the steps are: generate a uniform random number, computing it, and were commonly applied in Monte Carlo simulation for uncertainty analysis, effective in modeling random load behavior in suspension bridge components, simple, flexible, and widely used in reliable studies, right? So the inverse transform method. The inverse transform method is used to generate random samples from a known probability distribution. It works by first generating a uniform random number u, which is like belong to 0 and 1, then finding the corresponding value x equal to f inverse of u, where f inverse is the inverse of cumulative distribution function, that is CDF. This method is widely used in Monte Carlo simulations, which are applied in a load uncertainty analysis to simulate thousands of random load cases. Its advantages are simplicity, flexibility, and accuracy, making it ideal for modeling random loads in a bridge component and evaluating different stress scenarios. What is polynomial chaos explanation? That is PCE. Polynomial chaos expansion is an advanced technique to represent uncertain parameters using orthogonal polynomials. It approximates the response of complex system under uncertainty by expanding it in terms of random variable. In load uncertainty modeling, PCE helps effectively estimate the impact of random inputs such as material strength or wind pressure without excessive computational cost. So the polynomial chaos expansion is advanced uncertainty quantification technique. It expresses a system's uncertainty response as a polynomial series of random variable. Instead of performing thousands of simulations, PCE approximates the output response effectively, saving computational cost in a suspension bridge of modeling. PCE is used to analyze how uncertainties in parameters such as material properties, cable tension, and wind loads affect the bridge's overall behavior. The technique allows engineers to estimate the probability of extreme stresses without running time-consuming full-scale simulations. So now, transformation in load modeling of suspension bridge. So in the context of suspension bridges, variable transformation simplifies the representation of uncertain inputs like wind and traffic loads. By converting these inputs into standard probabilistic form, they can be integrated into simulation model with a great ease. Transformation enables the use of analytic tools such as readability indices and safety factors, helping engineers assess whether the bridge can withstand uncertain conditions. Moreover, joint transformation allow modeling or correlated loads. For instance, wind and temperature effects acting simultaneously, resulting in a more accurate predictions. So here the converts uncertain input variables, example wind, traffic load, into standard probabilistic forms, simplifies the integration of load effects and simulation models, enables use of analytical tools like reliability indices and safety factors, allows modeling of correlated random loads using joint transformations, reduces computational complexity while improving accuracy. So now we go for applications in reliability analysis. Variable transformation is crucial in reliability analysis of suspension bridges. By converting complex load distributions into standard forms, engineers can apply analytical methods to estimate the failure probability and safety margin. It helps predict how likely a bridge is to fail under uncertain conditions, ensuring that design standards meet reliability target. Okay, so reliability analysis aims to predict the probability of bridge components failing under the uncertain conditions. Using variable transformations, complex and irregular load data can be standardized, allowing for analytical solutions to estimate failure probability, safety margin, and reliability index. By applying these transformations, engineers can identify vulnerable sections of the bridge and plan preventive measures. These ensures that the design meets international safety standards and maintains functionality even under extreme or unpredictable conditions. So what are the challenges in variable transformation? Handling nonlinear dependencies between random variable, difficulty in determining accurate joint probability distribution, computational complexity for high dimensional problems, limited accuracy in extreme value or tail probability estimation, need for large data sets for precise modeling. So these are the challenges in the case study. In this case study, a suspension bridge subjected to variable wind and traffic loads was analyzed using random variable transformation techniques. The wind load followed a log normal distribution, while the traffic load followed a normal distribution. Using the probability integral transform PIT and PCE, engineers evaluate the total uncertainty in load effects and observed a 12% variation in stress distribution. The results demonstrate the variable transformation not only enhances prediction accuracy but also reduces computational time compared to traditional numerical methods, providing its efficiency in reliability based bridge decision. The conclusion of this project is this project shows the random variable transformation is crucial for accurate and efficient load uncertainty modeling in a suspension bridges. By converting complex or irregular random variables into simpler forms, engineers can perform probabilistic analysis with higher precision and lower computational efforts. Techniques like PIT, inverse transform, and PCE are powerful tools that help predict bridge performance under certain conditions, thereby ensuring structural safety and longevity. The study reinforced the role of probability and statistics in a modern engineering design analysis. So the references are like structural reliability analysis and predictions by R.E. Melcher, lecture notes on stochastic mechanisms by Armand D. Quergin, all these things. Okay, thank you so much.